Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third lecture covering material from Chapter 5. And while I try to pack as much of the important information into a small amount of time as possible, please do realize that in our actual lecture, we covered this material in much more detail and with some practice. So while I hope this is useful, please come to lecture. So we start this lecture and we're talking about heat or Q of a phase change. So we noticed in the previous lecture that when we go through a phase change, the temperature doesn't change. So I tried to draw, you can see over here a little bit of a heating curve, and this flat spot represents the phase change. So it's important to know what these phases are called, and one of them that's kind of confusing is fusion. Fusion means melting. So we're melting, we're going from solid to liquid. Going the other direction would be what we call freezing. So realize it's the same size along this curve. There's no change in temperature, but the value, the amount of energy it takes to melt or freeze is the same. But when we melt, we have to add energy. When something freezes, energy is released. So take a second to think about that. If we have a delta H value, the amount of energy to melt, that amount is the same for freezing with the different sign. So the other phase change, not on that diagram, is the vaporization, or going from liquid to gas. And going the other way, we call that condensation. So those are some important phase changes that you need to know. And since we don't have a change in temperature, we can't use our traditional Q equals MC delta T. There's no delta T. And so what we end up using is this formula, Q, the heat of this phase change, is the mass. And if I was melting, I'd have a heat of fusion. So that will be the formula that we use. You can see here we've got values given for water, and these values are typically given unless you're solving for them. So we've got a delta H fusion 333 joules per gram and a delta H vaporization 2256. And I just showing over here how if we're freezing or condensing, same value, different sign on that. So in example calculations down below, converting 250 grams of water, that's our mass, at 100 from liquid to gas. So it's really important that you draw these heating curves, and since this was water, we know the freezing temperature and the boiling temperature. We can write those right in on the y-axis, and it's nice to just map out where we're going here. So we're at 100 liquid to 100 gas. So this is the phase change going from liquid to gas. So right here, like in the middle of this, both are present, liquid and gas. If I was at one extreme, this is just pure liquid at 100, and this is pure gas at 100 over here. But if a question asked you, what is present here, this would be liquid and gas phases both. So back to the question, we've got Q equals mass times the delta H of vaporization in this case, and we're vaporizing, we have the value, and we can solve for Q, end up with units of joules. Oftentimes you'll be asked to convert to kilojoules. You definitely want to be able to convert from joules to kilojoules for this chapter. This question's a little more complicated. It's again, we want to build that roadmap and see that we have water. So I know my freezing point 0 degrees, my boiling point's at 100 degrees. We're going to start at 40 degrees. So I put a 40 in here, and I didn't measure it. It's not that important. I need to be between 0 and 100. So I'm starting here, and I'll write this right out before I even do any of these problems. So I'm going to steam at 100. Steam is the gas phase. So I'm going to go up to the liquid at 100, and I'll use Q equals MC delta T to determine how much energy this is. And then I have to go through the vaporization process where I use Q equals mass times delta H vaporization. So no change in temperature there. So this is just worked out. You can take a look at this. Try to be able to reproduce this on your own. So another question here for you. We're going to melt 500 grams of ice at 0 and then heat the resulting water to steam at 100. So, again, draw out this heating curve. We're going to start here at ice at 0 degrees C, and we're going to end up here. So this is going to require one calculation here. The second calculation here, we'll use Q equals MC delta T, and the third calculation, we'll use Q equals mass times the delta H of vaporization. The constants are given. And I've got the work here on the next slide, so you can take a look at this. Another good question to practice. If you can do both of those on your own, you're in good shape. Do be prepared for maybe an object that's cooling. And we can use the same diagram. We're just going in the other direction, and be aware of your signs. So the next thing we talked about were enthalpy diagrams, and sometimes we call these potential energy diagrams. And it's just a way of representing the energy or the enthalpy of our reactants and products. So instead of writing the reaction like we typically do on one line, we write the word reactants and we place it at the energy scale. So what this one is showing is our reactants have high enthalpy or high energy, and our products are lower. So, it's just like we typically write a reaction, reactants, arrow, products. Well, now we're scaling these in terms of how much energy they have. So we're going from high energy to low energy. This means energy must have been released. So this is an exothermic reaction here. So delta H, remember, final minus initial. So if I had some values in here on the scale, and I don't, but I could write some numbers in here, this would be a lower number than this. And so the delta H, products minus reactants, final minus initial, I can think of. So this is going to be a small number minus a big number. This is going to have a negative delta H, which is also consistent with an exothermic reaction. So, of course, we have an endothermic system here where now the reactants are at lower energy than the products. So energy must went into this reaction to make this happen. And you can see I did put a scale in here, and I just made this up. So we've got the delta H, final minus initial, or products minus reactants. That's going to be 100 minus 50 kilojoules. Our delta H would be a positive 50. This is endothermic. We're going to come across these delta H values in a lot of different formats here over the next couple lectures. So I just wanted to kind of call them out, and don't get too hung up on this slide right now, but realize that we're going to see some different changes in energy. This one, the first one, is for a reaction, the way the reaction's written, and we'll dive into that a little bit today. But we're also going to talk about molar enthalpy and, the enthalpy of 1 mole of a substance. And this enthalpy of formation is another thing we'll get into in some detail later. But don't get hung up on this now, but come back to this maybe when we're through the entire chapter and just make sure you're comfortable with those 3 types of delta H. So getting into delta H of the reaction, what we're showing here is a reaction, CH4 and 2O2 going to CO2 in water. This is a combustion reaction, and we have a delta H reaction, and it's got a negative value, which means that it's exothermic. So we can write that value right into the equation if we like. Sometimes that's useful. So if energy is being given off, that would suggest that the energy is a product of this reaction. So I can write it in on the product side. And the value is positive now because it's on the product side. We know that that's being produced or given off. So that's why the value is positive 802 kilojoules in the reaction. So we're just treating it like it's a product. Now what we've done is we've brought back reaction stoichiometry with an energy value. So I have 802 kilojoules is equal to 1 mole of CH4 for this reaction, or 2 moles of O2, or 2 moles of H2O. So this can be very useful to figure out how much energy is released when different quantities are used. So that's where we're going to wrap this up. It was just a typical question where we're starting with grams, grams of methane. So we've got this equation. I rewrote it and put the energy into the equation, same as before. And so I'm starting with my grams and converting to moles, just using the molar mass of the CH4. And then I'm going to use that factor that I've got from the reaction. So this is reaction stoichiometry, 1 mole of CH4 in the denominator. To cancel moles of CH4, I've got my 802 kilojoules in the numerator, and the answer is 6424 kilojoules. And this would be a great problem to kind of jot down and try on your own. And you can come back and look at this if you're having trouble with it. So best of luck, and thanks for watching. Please give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor's DuBois channel.